In the previous section, we looked at the role IT professionals play in supporting scientists and their interaction with groups of people that they will be in contact with. In effect, the political side of support. Now we're going to look at support through the eyes of people who do it successfully on a daily basis. Before we get into the basics of supporting and troubleshooting the labs, it is important to understand some very basic principles. The scientists are generally very intelligent and capable people. Many of them have computer skills. Don't be surprised if they indicate your services aren't needed. While they may have basic skills or even some advanced capability, they don't work with these systems on an administrative level every day. Troubleshooting issues is generally what any IT person spends the majority of their day doing. Even though you own the high ground when it comes to computers, it is extremely important not to be perceived as being authoritative, a know-it-all, or condescending. You are there to support their efforts and lend your knowledge and advice as a best practice. Consider initial interactions as a testing phase. They will decide quickly if they want to interact with you at all, or just out of complete necessity. The more successful you are in supporting the labs, the more it will make you an invaluable team member. You'll be on the good side of the lab manager, and you'll start to get advance warning of initiatives that affect IT. As a result, your work will be far more rewarding. It is very important to avoid using no as an answer to a request. If the scientists are asking for something that goes against corporate standards, it's up to you to inform the scientists that there is a corporate standard, but you'll work with them to find an appropriate workaround, something that's supportable. You're their advocate to the corporate IT structure. The more you understand what they are trying to achieve and how they work, the better your advocacy will be and the more you will be valued by the scientists. Communication is key. Inform them of when and what and how you'll be doing work in their labs, keeping them up to date, and provide follow-up. This is a matter of customer service. We provide support. Everyone likes courteous, white-glove treatment. Be proactive. Demonstrate your commitment to solving the issue in the most expedient fashion. This means acting with urgency and attention to detail. Exude your confidence. Demonstrate your skills, experience, and knowledge. Confidence goes a long way with users who have instruments that are often priced at over $1 million and are used in critical studies. Respect. Make an effort to understand what their challenges are, what they do, and how they do it. This shows that you care, and it's important to you as well. You're there to support their mission, not just solve a problem. Always seek to establish trust and rapport. Get to know people, learn their names, what team they belong to, what they're working on. And always work to defeat the geek stereotypes and expectations many users and the scientific people have of IT. Scientists are curious and always eager to learn new things. Indulge them by explaining or sharing some IT knowledge with them. Explain how you fix the problem, but do this in everyday language that they can understand. Use metaphors or analogies where possible. Never be patronizing or condescending. Scientists are smart, hardworking people. Act accordingly. Never underestimate a scientist's knowledge, or even their IT knowledge. Don't be afraid to deliver bad news. When you do, make sure you know the facts and have a backup plan. Plan B, C, D, E, whatever. By giving them options, they feel in control. Once you give them options, you can say what scenario is more supportable by IT, but it must meet their requirements first. Never be afraid to mention that there may be better alternatives to doing something that could provide more benefits. If you do, make sure you have the specifics and can follow up. It's okay to say I don't know or that you don't have the answers, but that you will shortly, and then follow through. Give status updates when outstanding items linger. Make sure there's closure. Scientists are busy people. Your best tool in your IT skills bag is troubleshooting. Get in, get the facts, state your plan, then get out of their way. Be efficient. Strive to exceed expectations. Move beyond the break fix, just get the ticket closed mentality. If while fixing an issue you see other problems, something where you can make a difference, mention these and get to work, even though this may double your workload. You may fix a much bigger problem before it becomes one. Your engagement is more about the long term than quick wins. Be available and responsive. Scientists hate having to wait for days or even weeks just for someone to show up. Whenever possible, do the work in person. This is critical. Scientists love to talk to a live person, someone who makes the effort to come to their lab and work on their stuff. It also says to them that they have a local expert they can depend on. Even if you can remotely fix a system, take the time to go in person. Once they understand they can rely on you, the remote fix option will be more easily accepted. Activities in the lab will almost be guaranteed to run contrary to corporate policies. There may be a need to create segregation of the lab in some capacity, but the separation creates different problems. The life cycle of lab instruments, companion systems, and the software run far longer than typical corporate systems. When the corporate changes policies on minimum operating systems, database versions, antivirus, backups, or other platforms, security, or management systems, the labs will inevitably be impacted. How to deal with the outliers can become a bone of contention between the corporate IT structure and the scientists. Changes in policy impact budgets and create unexpected work to adapt to the new policies. Vice versa, scientists do not often think about the impact of ordering systems that need to be integrated with the network without talking to IT first. This can create an impact into IT's budget and resource pools to facilitate the request. It is important to explain why corporate IT needs to periodically change these policies, platforms, and tools to stay current. But for the most part, the labs are the business driver and need special consideration and a more complex support structure. This brings up the Bridge IT team, or Lab Support Specialist concept, that can bridge the gap between traditional IT models and the scientists. An IT group that specifically supports the labs and understands the needs of scientists. IT people with specialized skill sets for specialized IT support. IT needs to be a strategic partner. It's important to remember that the science is the business, and the operations group need to be at least aware of the needs of the labs. Lab ops, IT lab project management, etc. can work to find a common ground between corporate IT requirements and science requirements. When you enter the labs, you'll find many different types of instruments. We'll look at several. The first are the ones that are off the network. These are standalone instruments with or without a companion computer. They are typically off the network for a reason. They often have printing capability to generate test results. Keep in mind the system may have been on a network at some point and was taken off the network for various reasons. Authentication is almost always local authentication, if any. Don't be surprised if there is one shared account, even if that runs contrary to corporate policy or the FDA's 21 CFR Part 11 compliance requirements. This can be pretty common, especially in academic labs. The PCs may not have been on a network. Data saved to an external hard drive, or the PC gets retired when it becomes full. People often use external storage like USB drives to store data. Some are designed to be standalone and cannot be joined to a domain or network. Some have odd hybrid PC systems where an external PC talks to computers internal to the instrument, and again cannot be added to a network. Some have older operating systems such as NT4, or are based on Apple's Macintosh systems. They also could be a vendor-supplied PC that is not supported by the corporate IT team. Some organizations leave these to the scientists to manage. You'll also find instruments that are on the network. These systems are networked and often part of the corporate authentication domain, or a trusted or segregated authentication domain. You will often find typical IT tools such as antivirus on the system. These systems are easier to maintain and perform routine maintenance on with typically available tools, but will inevitably have more problems. For example, antivirus, firewalls, and other corporate security tools can interfere with the instrument software and/or data acquisition. Antivirus updates and operating system patches can cause problems. Domain accounts. The data can end up sprawled across a user's Windows profile. Because a PC is on a network doesn't mean it can save data across the network directly. Instruments can have bandwidth issues across a network, or if there's a network glitch during data acquisition, data can be lost. Some systems live on a small, private network. You will see one or more instruments, some companion computers, and maybe even a printer. These little ecosystems usually come from the vendor in this state, and this is the only way they are willing to support the application. You will usually see a little switch or hub connecting these systems. Sometimes the switch is uplinked to the lab network so the scientists can get the data out, even though they break the vendor's supportable configuration, or be unaware of the risk exposing unprotected systems to the lab or corporate network. Private networks can also be set up for manufacturing systems, which limit access due to data security reasons. However, this can make data backup a challenge because private networks often do not have any backup technology. Some systems with private networks cannot be joined to a domain. Instruments will be connected to companion computers with many different types of data connections. You will see parallel, serial, USB, coax, Ethernet, and others. The companion computer systems are typically supplied by the vendor if the connection has some proprietary design such as a special PCI card or required operating systems or software configurations. You must be aware that the application running on the system typically hasn't been built to be a robust enterprise application and cannot weather the storms of a typical corporate computer. You will see functionality via DICOM, usually sockets, or even a complete relaxing of all basic security parameters. Time permitting, you should spend some time documenting the connections between the instruments and the companion computer. Take pictures. Put small color-coded stickers on cables and connection points. Also, as a vendor updates its technology, the interfaces and communications methods may change. If an old system fails, users may find that their hardware is no longer supported. To restore the system, they may not only have to upgrade the software, but all the hardware as well. If they do not have a service contract in place, this can be expensive. This brings up issues around warranty and service contracts, which users often are not great at keeping records of, or keeping them up to date. Many forego them, thinking they are too expensive, but this can be short-sighted. Having a service contract may mean getting up and running in hours or days versus weeks. Create a lab support email account and schedule. Depending on the size of the organization, this idea may not be practical, but take the principles of this and apply them to your organization. For the support team, everyone should have access to this email and calendar. Lab support tasks should be routed to this email account. Different support personnel should mark each issue. For example, Microsoft Exchange and Outlook allow you to color code, everyone owning a specific color. This way you can see who owns what issues and also see which issues haven't been addressed yet. The equally important part is the calendar. The calendar should be used to map out routine activity with a complete description of real-life expected time to completion. This shared calendar will not only give visibility to what needs to be done when people are on vacation, sick, or for some other reason unable to perform their duties. Also include activities such as mandatory training on the schedule for everyone. Having these routine tasks in all the group calendars will help with project planning, budgeting, and staffing the service appropriately. It can take over a year to build this calendar to what it should be. Don't get discouraged. The long-term gain is well worth the effort. This is an example of a very rudimentary system, but an example of one approach that's been used inexpensively and successfully. Lab IT support needs to have an organization behind it, with a strategic role and authority to perform its function in collaboration with the scientific community and other business partners, as well as corporate IT. Lab IT staff need the appropriate tools to function: knowledge bases, help desk systems, asset and tracking tools, documentation, and so on. Understanding the usage schedule of instruments and any companion systems is very important to work effectively in the laboratories. Some systems may not look like they are in use, but some tests run over periods of days unattended. If you find a system locked, don't unlock it without asking the person who has a current session if it's okay to log them off. This may impact your ability to perform the work you want to do, but it's better not risking interfering. Instruments may only become available for short periods of time each week. Adjust your schedule to attend to these windows to do your maintenance tasks. The schedule might change from day to day and week to week. Verify that a piece of equipment isn't in use before proceeding. Don't start any activity you cannot comfortably complete before the instrument is needed again. For these ad hoc windows of support or maintenance opportunity, add a task to the group calendar to contact the instrument owner to ask for the weekly IT window. Make this request a recurring task in the actual work a tentative recurring meeting that can be moved. A schedule that tracks operational tasks is especially important when working within a GXP environment. Standard operating procedures customarily outline specific tasks and iterations for those tasks. The schedule will keep you in compliance. When you are working on a problem, always ask someone to show the issue. Schedule a meeting, specific time and specific place for that to happen. Always have the user show you the problem and explain it from their perspective. Also try to get the user to remain available for questions and review things before attempting a fix, or if you encounter further problems. Having the users present is like having a witness. Scientists can be like anyone else and can point fingers. Before making a change or a fix, review it with them and then ask if it's okay to go ahead. This isn't meant to be a negative thing. Done right, it involves the user in the process. It can actually be empowering as they have a chance to give their input. It helps them own the solution. As always, it's an opportunity to impress them and make their day a bit easier. It is essential to create a wiki or knowledge base for the lab support. This can be done in many different ways, but you need something that can be easily searched and organized. From an IT perspective, the labs can be viewed as a Wild West, but it isn't structured that way for the scientists. IT needs to look at the labs through their eyes and create robust documentation so that more than one person can support it. Inevitably, there will be a series of spreadsheets used to document instrument issues. Depending on the size of the labs and number of instruments, keeping them current should become a scheduled task. Someone should periodically review service tickets and projects and update the documentation. It's also good to verify who is working on which instrument. Having only one name associated to an instrument can lead to orphan instruments and software when that person leaves the organization. This equipment could be potentially reused in another lab, shut down in coordination with the lab manager, or the instrument user list can be updated by having it assigned to someone else. While knowledge bases are often helpful to complete work, leveraging work practice documents that explicitly describe how to perform a particular process can be more helpful when working in large groups. The downside is that these can take a lot of time and effort to create. However, they may not be useful for unique troubleshooting situations. Cross-training is essential. You should never have a single person with all the knowledge in his or her head. Communication among team members is critical, so everyone stays up to date on developments. This can help people prioritize and anticipate, share knowledge, and work more effectively. As you make your way around the labs, it is important to document the instruments, their general location, and ask the people in the lab who uses each piece of equipment. At an advanced level, you can start asking how the instrument fits into the general workflow of the bench or the laboratory, so that when a problem arises you can understand how this instrument fits and the impact of the issue. The trouble ticket may appear to only have a minor issue to a help desk, but once you understand the workflow, you will have the ability to understand its true impact and reprioritize when needed. An issue to a lab system could be categorized as impacting one system, but in fact it could take several people, an entire lab, or even part of the manufacturing process offline. How do you communicate this knowledge? The typical way is to do inventories in Excel, but these are obsolete before they're even finished. The best solution is to have an asset tracking system to track instruments, install software, warranties, service contracts, and so on. It can track service history, prompt for any renewals, and preventive maintenance visits. The system should use barcodes or RFID to automatically detect when new instruments are added, moved, decommissioned, etc. Again, there should be, ideally, a lab IT organization that has the tools to perform these functions. You may get a request like, how many instruments of a certain type do we have? How many copies of a particular piece of software do we have? Or something similar. If you do this physically via manual inventory, it could take weeks or months to complete. Or you can run a report in an asset system in a few seconds, which makes more sense. Track who uses each instrument. Lab instrumentation can be heavily used one day, and then not used at all for a long period of time. It's not uncommon for one lab not to know what's going on in a different laboratory. Since you are a resource that traverses all labs, you can be a key communications point for scientists. One lab may have no idea that there are unused plate readers in another lab, and then they go off and order new plate readers to fill a perceived need. There might be some resistance to having IT control instrument inventory, so tread lightly here. The same goes for the instrument software. Typically, the labs do not have strong controls of the distribution of software. It's easy for labs to go over their allotted licensing without someone keeping track. There are good tools out there for keeping track of licensing, but all of them require the systems to be networked. Scientists can be very possessive about their instruments, and often act as if they own them personally. Bear in mind that some instruments are very expensive, and the users have had to wait a long time to get them. So often, they don't like to share. However, if an instrument suddenly becomes obsolete because the person who wanted it got fired, then that instrument becomes dirty laundry, and users tend to keep quiet about it. As the IT person, how do you handle this discovery? Note, if it has critical data, you may have to maintain it, and government regulations may require it be maintained for as long as the project lives. Groups not knowing what each other is doing is much more relevant in terms of projects. It is very common for more than one group to be doing exactly the same thing, and yet not know this. In some organizations, this occurs because people want to protect their interests. These projects may involve the need for the same or similar technologies, but their goals and needs, at least as they perceive them, can be very different. At some point, as the IT person, you become aware that this is going on, and you're left with a very delicate political bomb. Should you propose to find a common solution to their IT project needs, one or more groups may feel that they've been ratted out by IT. So, take negotiating skills carefully to deal with this properly. Track all documentation that comes with an instrument, as well as licensing information. You can scan this information and save it all in electronic format. Also track license usage and enforce that license usage. Enforcing license usage in places that have no way of tracking what they've used or purchased can be difficult. To bring users into compliance can be tricky, because you may have to approach people to give up a license to make things work, or impact their budget for unforeseen expenses. Vendor management is a key component in lab support, and can include software, instrumentation, or enterprise systems. Vendors can be a lifeline in your role of support and help resolve issues in a timely fashion, or when issues are completely beyond your skills, such as instrument failure, preventive maintenance visits, and so on. Unfortunately, how each vendor honors its support obligations can vary widely, as can the methods you need to follow up to request support. If you go through the front door to request support, that often means calling an 800 number, waiting through support options, and then finally getting someone online who just takes your name and number and says someone will call back. Meanwhile, the users are waiting in the labs with a down instrument. The solution to this is to work with a vendor and identify key knowledge experts within their company who can expedite your request for support and information. Cultivate a solid working relationship with these people. Assist them when on site, and make sure they receive the resources they need to help make their job easier. In return, You'll often get their direct numbers and contact information, and thus, when you really need immediate support for an emergency, you can call these people directly. The end users, who are used to long delays and wait times, suddenly find their support has been fast-tracked, and this can mean the world to them. Vendor management can also mean that you have an understanding of how the vendor works, its culture, who all the lead reps are, how they structure their support and service work, and contracts. All of this is designed to help you support the end user better. Communications and information is key to scientists. Having a strong working relationship with a vendor makes everyone happy. Understanding workflows in the lab is useful, and they can be viewed at two levels. The first is the bench workflow. Several groups could be working within the same laboratory space. Their activities may or may not have anything to do with each other. Typically, a lab bench is part of one workflow. Understanding how the instruments are used, in what order, and then who uses each instrument will be helpful information when trying to arrange maintenance or get answers when scientists are not available. The lab workflow is a larger entity. This is very similar to the bench workflow, but the entire lab might be involved in that, not just a single lab bench. The lab workflow may extend to other laboratories. It is more important to understand the workflow at a high level and then map its physical boundaries. Once you have an understanding of the fragmented workflows on the bench or in the lab level, you can then piece together the fragments together. You should be able in time to map equipment usage from discovery to manufacturing. If your primary role is to provide instrument support in the labs, you may not need to know all of the details of the workflows. Sure, it's helpful, but these workflows can be highly complex and can take a long time to learn them. This knowledge may not directly impact your ability to troubleshoot an issue with a single lab instrument. However, on a project or enterprise systems level, it's another story. Knowing workflows is critical if you support or implement an enterprise platform or a department-wide project. By mapping people to instruments and workflows, you've taken into account the business process and the general methods of getting laboratory work done. Since your background is IT, you'll need to map the technological dependencies. These mappings are essential to quickly and accurately map out changes. Having a list of software packages in use is essential. Populating this list with known compatibility limits for platforms will help lifecycle planning. But the key to the dependencies is mapping how these instruments and instrument companion systems integrate with the surrounding network. Key areas include backups, network shares, authentication, antivirus protection, patching, upstream and downstream systems for data automation, network connections, as well as things such as DNS, WINS, ERP, LIMS usage, ELNs, scientific data management systems, and EDC or MES systems. These dependencies fall into two categories, IT and scientific dependencies. It's important to have a good handle on the IT portion, as the scientists will be of little help in understanding these. When there's a change in the labs, the scientists will have a much better handle on the scientific dependencies, but it is important to also know them, since some of the integration descriptions might be IT in nature and undecipherable by the scientists. If the overall picture isn't clear, it can lead to unexpected complications during implementation or migrations. Regulatory compliance. Understanding which systems in the labs are compliant systems will help you from invalidating those systems. With teams working within the labs, keeping track of compliance systems can be difficult. There are a couple of ways to keep people informed of which systems are under regulatory controls and which are not. Have a system naming convention that identifies regulatory systems. Make the background color of any online information an identifying color so that they know it's a regulatory controlled system. Create a login message warning the user that it's a regulated system when you log into the computer. Also add physical stickers or markings on the system itself. It's almost impossible to inform people of the system's regulatory status in all connection types, but by protecting common access methods, you are making attempts to protect and keep them informed. A general rule for IT lab work is, if you don't know, then don't do it. If you don't know how, then ask. This is all the more applicable to regulatory environments. The rule here is to always have an abundance of caution. Always check with people before changing anything in a validated environment. As a rule, though, it is assumed you won't be in a validated environment unless you are trained, approved, and given access. But even then, always ask first before changing anything, followed by an "Are you sure?" question. In half the cases where you may ask this question, you may get this reply: "Well, perhaps we should check with someone." And when you get the answer, you may prefer to put it in writing. And here's where a wider system understanding can be a big advantage, because the users may not be aware of the full extent of what is validated. They often just see the instrument right in front of them and fail to take into account infrastructure and so on. Their method of working may not change between non-compliance environments and regulatory environments, so they may not even be aware of the distinction. Before you work on compliance systems, make sure your training is up to date. If your training isn't up to date, only work on the system if it's an emergency and you receive approval from someone in quality assurance. Try to change tasks with someone whose training is up to date for the work, or have someone else who is trained perform the actions and you assist. It is a personal responsibility to keep your training up to date and be aware of the standard operating procedures, scope, and roles and responsibilities. Any activity that runs outside of the SOPs may require change control. The IT department should sit with compliance and lab managers to find gaps in the SOPs and effectively support the labs. Depending on the situation and the scope of your involvement, they may decide you'll have nothing to do with the software, and they will leverage corporate IT's ticket system to maintain qualified states of the host system. In this case, it is critical to keep a record of all activities on the host systems. Most companies are not accustomed to IT people working with instruments and only have partial exposure to companion systems. It wouldn't be surprising to see raised eyebrows, concern, or resistance to IT involvement. By knowing your role and the responsibilities within standard operating procedures, you'll be able to help the organization maintain the state of control needed for regulatory systems. It's not uncommon for there to be gaps or assumptions made. Core IT groups may also make a policy change and be unaware of the impact on compliance systems in the lab. This puts the IT person in a tough spot between the department that pays their salary and the compliance required to maintain a regulatory state. As outlined in the previous slides, staying within the SOPs is vitally important. When working with non-validated systems, you must also acknowledge that there might be a chance the system may become a compliant system. Doing validation retrospectively can be an extremely costly endeavor, but it's always a possibility. Make sure you document all of your activity in the available ticket system or keep a running log. The goal of validation is to maintain a controlled state. It is very uncommon to validate the operating system or anything outside the software. Maintaining the records for all IT-related activities gives not only compliance groups comfort that IT is in control, but also the lab manager. This is the end of the first section. The next section, Part 2, will get into more technical details of understanding data formats, backup strategies, how to carry out maintenance and troubleshooting, what's involved in deploying new systems, and what steps you have to take in working with the customer and the vendors, and finally a wrap-up.